Hello. Today we're going to be going through Chemistry Chapter 1, an Introduction to Chemistry. Okay, so first let's start on Unit 1.1, Chemistry, the Science of Matter. Okay, so first off, let's start with what is chemistry? So chemistry is defined in your book as the branch of science that deals with the composition, structure, and properties of matter and the changes that matter undergoes. So composition has to do with what is there. Structure has to do with how it's arranged. And the properties are things such as boiling points, and it's like viscosity and that type of thing. And then the changes would be its reactions. And we'll get into those terms more as we go throughout. So chemistry has 5 major branches. There's physical chemistry, which is a lot of, it's kind of a physics meets chemistry. There's a lot of quantum mechanics involved in there. Organic chemistry, which is the chemistry that involves anything that has the element carbon. Inorganic chemistry, which is anything that does not have the element carbon. Biochemistry, which has to do with chemistry pertaining to life. And analytical chemistry, which looks at finding out how much of a different substances in different samples and does tests. Think like a forensics scientist. So where does chemistry apply? Well, there's some examples of chemistry in your everyday life. Whenever you look up in the sky and see stars, you're seeing something that has to do with chemistry. Whenever you pet an animal, chemistry. The pencil or pen that you use to write is chemistry. Computers use chemistry. Tables also use chemistry. Anything made of matter uses chemistry, which is practically everything you will ever encounter. So, actually, not even practically, it is pretty much everything you will ever encounter. So, now that we've talked about chemistry, we said earlier it was a branch of science, but what is science? What does that mean? Well, science is the systematic study of God's universe and how it works. To do science, we use what's called the scientific method. So in the scientific method, we first observe. We take measurements, we collect data, we study the literature, and do stuff like that. That's more when we collect everything and get it ready. And then we hypothesize. We look at all of our results and make a guess or a tentative explanation, as the book states. And then we want to experiment. So we set up a controlled situation where there's only one variable and everything else is constant. So a variable is just something that can change. So for example, temperature could be a variable. If you want to see how something reacts in different temperatures, you hold everything else the same. So you use the same container, you use the same amounts, and you just change the temperature. So that would be an example of a variable, and then everything else would be constant. So there's also a bit of a discrepancy between what a theory is and what a law is and what people think of theories and laws. So a theory is a hypothesis that is supported by empirical data. Empirical data just means data that has numbers to back it up. They've done the experiments, they have the numbers, and it supports it. That's empirical. A theory can be proven false by just 1 or 2 experiments. A scientific law is simply a theory that has stood the test of time and is supported by irrefutable empirical evidence. Now, some people will think that if you hear the term, oh, it's a theory, like, oh, it's just a theory. It's something that people say a lot. However, a theory is not just a theory, as in it's not just a guess. A theory is supported by a lot of evidence. For example, a famous theory that isn't a scientific law yet, but for all intents and purposes would be the Einstein's theory of general relativity, which was, I believe, in the early 1910s, I believe, was when he first came up with it and published it. It might have been a little later on than that. I confuse special and general relativity when they came out. But anyway, that's not really important. In the scientific consensus, Newton had his view of gravity, and he had his equations and his laws. But then, so there's the law of gravity. But then Einstein came along, and he shifted the entire paradigm and kind of proved that while gravity was true, there was something deeper going on. And that's what he did with relativity, without getting any into what relativity is, because it can be a little confusing. So generally, when a scientific law is broken, it results in a giant paradigm shift for science as a whole. So we used to be thinking one way, and now we think a completely different way about gravity, for example. So that's the end of section 1. Let's move on to section 2. This is measurement in chemistry. So the first thing to realize about measurement is that there is a certain amount of ambiguity whenever you measure something. And we will cover that more in depth, what I mean by that, when we go on to section 3. But for now, just accept that there are two types of numbers, those obtained by counting and those obtained by measuring. If you count something, it is exact, it's called an exact number. If you measure something, it's called an approximate number. So, yeah, we'll get into that more later. So defined numbers are exact always. So what's a defined number? Well, you could say a dozen is 12, right? That's a defined number. So if you say a dozen, you know it's 12 exactly. It's not 12.01. It's not 11.5. It is 12. So defined number is exact. And counted numbers are also exact, but any measured numbers are approximate or inexact. So in measurement, there's two concepts that are important to understand. So there's precision and accuracy. And I'm sure you've already had this repeated you many times, but in case you haven't, let's go over briefly what the difference is. So precision is your consistency or repeatability in a measurement. Accuracy is how close the value that you've been measuring is to the actual value or the correctness of your measurement. So as you can see in the example here, in the top left, there's low precision, low accuracy. In the bottom left, there's high accuracy but low precision because they're kind of spread out. In the top right, there is low accuracy because they're not at the target, but there's high precision because they're all clustered. And then in the bottom right, there's high accuracy and high precision because they're all on the target and they are very clustered. So let's talk about systems of measurement now. So what that is simply a collection of compatible units that can be used to measure different things. Now, those different things can be temperature, they can be time, they can be length, they can be volume, they can be mass, anything like that. So in science, we use what's called the metric system, as I'm sure you've heard of before. Now, the metric system is nice because it uses prefixes and base units to measure quantities by orders of magnitude or powers of 10. And we will get more into that. I have a supplemental video that kind of covers how to convert in that. But for now, you can just kind of look at this here. You can see the different units. So for mass, the SI unit, it's the kilogram. For length, it's the meter. For time, it's the second. For current, it's the amp. For temperature, it's the Kelvin. For luminous intensity, it's the candela, which you probably won't come across very often. And for the amount of a substance, it's the mole. That's a very important one to know for chemistry. Just the thing to note out is that the kilogram is the SI unit, not the gram. For everything else, it's the base. Except for mass, it's the kilogram. So just make sure you know that. Okay, and this here you can see, this is how the metric system works, is it uses prefixes. So in the middle there, you have your base unit, and then as you go up and down orders of magnitude, you get different prefixes. So For example, if you go 3 orders of magnitude or 1,000 times up, it's a kilo. If you go 3 orders of magnitude or 1,000 times down, it's the milli. So a millimeter is 1/1000th of a meter, and a kilometer is 1,000 meters. So just some miscellaneous notes. Let's talk about mass versus weight. So mass is the measurement of how much matter is in an object. Weight is a measurement of the gravitational pull on that object. So while they're similar, they're not the same. Mass remains constant no matter where you are, but weight fluctuates based on what planet you're on, or if you're on a planet at all. For example, on Earth, we have a mass and weight that are essentially the same. But if we went to the moon, our mass would be the same as it was on Earth, but our weight would change because the gravitational field is different. Let's talk about quickly the formula for density. So the symbol for density is rho. It's a Greek letter, and it looks similar to the letter P in the English language, but it's not. It is rho, and it is mass over volume, or M over capital V. Little v is velocity, but just remember mass over volume is density. And then here's the equations for temperatures in Celsius, Fahrenheit, and Kelvin. Of note is that to change to Kelvin, you just take the temperature in Celsius and add 273.15 degrees. What's nice about Kelvin and Celsius is that their units are the same length, I guess would be the correct term. So 1 degree Kelvin, if you change by 1 degree Kelvin, you also change by 1 degree Celsius. They're just shifted by 273.15 from each other. So in chemistry, or in science in general, there's a thing called dimensional analysis. And now you've been doing this for a long time, but you probably didn't know what it was called. So anytime in school or in life when you've had to say, hey, I have 3 feet, how many inches is that? Or how many yards is that? You've been doing dimensional analysis, even if you didn't know it. So dimensional analysis is just a technique used to convert one unit to another, and it does this by using what's called a conversion factor. So a conversion factor is simply using a known relationship to get a wanted unit from a given unit. So in this example here, there's given unit times the desired unit over the given unit equals the desired unit, because the given unit cancels out and you're just left with a desired unit. I believe the next slide will have more information on this. Yes, so here's an example. So if we wanted to change 3.5 feet into inches, well, first we have to say, what is the relationship between feet and inches? We know that 1 foot equals 12 inches. So if we use a little bit of algebra and we treat that like an equation, we can divide both sides by feet. So we get 12 inches over 1 foot equals 1. And now we can multiply anything by 1 without changing its value. So we take 3.5 feet times 12 inches over 1 foot, because that is equal to 1. Now feet cancel out, and we get 3.5 times 12 is 42, and we're left with just inches. So that's how we use dimensional analysis to get from one unit to another. Okay, now let's talk about the mathematics in chemistry. So we use what's called scientific notation. So this just uses exponential notation to indicate the order of magnitude of a number. So when you use scientific notation, there should only be one value to the left of the decimal point in the what's called the exponential form. So large numbers are written as positive powers of 10, and small numbers are written as negative powers of 10, because if you remember from algebra, a negative exponent just means you divide it. So it's the same as just as dividing by 10 if you raise something to a negative power of 10. So the power of 10 shows how many digits we move the decimal point. And now that probably was very confusing, so let's get to some examples. So this here, what is this? 100,000 million, 120 billion, 400 million. That's 1 0.204 times 10 to the 11th. So, and by writing it in this form, the times 10 to the 11th, we save ourselves a lot of work, and we can very easily look at it and say, oh, that's has an order of magnitude of 11. And then the same way, if we have very small numbers, we simply move the decimal point and have it to the negative. So let's see, I hope you can see my mouse here. So how we do this is we can go, okay, so here's the decimal point. So we can go 1, 2, 3, 4, 5, 6. And now there's one non-zero digit on the left, so that's where we stop. So, and if we go to the right, we know it's a negative number. If we go to the left, we know it's a positive number in the exponent. And then here's another example. And this number here is significant because it is the speed of light. So that's how many meters per second light travels in a vacuum. Okay, so now let's talk about significant figures, because we kind of very briefly went over the concept of why we need significant figures, although we didn't really know it at the time. So let's kind of go over what they are and why they're important. So significant figures are just the meaningful digits in a number. So let's look at this example over here on the right. So if we want to get the measurement of this flash drive, if we look at the top here, we can say, well, it's somewhere between 2 and 3. Maybe it's 2.5, maybe it's not, I'm not sure. So we know for a fact it's between 2 and 3. But do we know that it's 2.5? Not really. It could be maybe 2.49, something like that. But how we say in science is we say you can go one decimal place beyond what you know for a fact. So in here, we could only say, okay, so it's let's say 2.5. That sounds about right. But if we said, oh, it's 2.4789, 32, well, anything beyond that initial 2.4 would be meaningless to us. All those other ones are just a random guess. They don't mean anything, so they wouldn't be significant. But then if we go on the bottom there, you can see there's more gradient marks, or more graduations. So here we can see more that, okay, maybe it is 2.5 for sure. Just looking at it here, it could be, maybe it's 2.49, but we have the 2 and we have the point to get to the 5. We can have one guess beyond that. So we can say, oh, it's 2.49 or 2.48, something like that. So when using sig figs, there are some rules if you see a number on its own. So the first one is all non-zero digits are significant. So if it's not a 0, it's significant. Zeros at the beginning of a number are not significant. So an example of that would be if we go back here, this second one, all these zeros before, they're just used to tell you where it is in the number, like what decimal place it's at, but they're not significant for the value of the number itself. But let's see here. But zeros between non-zero digits are significant. So let's go back to that example. See the top one there? You need this 0 in the 1.204 to know where that 4 is. So it has to stay there. And then zeros at the end of a number that has a decimal point are significant. So, and you might say, well, why is that significant? Well, if I have this here and I say, okay, that's 2.5, and I think it's 2.5 exactly, I can say, oh, that's 2.50. That tells whoever is looking at my results that I didn't just make a guess based on this top one. I had these other graduation marks here, so it says that it's more precise, or more precise or more accurate. You have a greater degree of certainty about that number than if it was just from over here. Okay, so in chemistry and just in life in general, here's a good problem-solving strategy. So when you start a problem, you should ask, what is known? Or, where am I? So you can look at what the problem gives you. And then you ask, where am I going? Or what is the problem asking? So where do you want to go? And then you say, well, how can I get where I want to go from where I am? So look at all the different paths that could get you there and then choose the best one or the easiest one if you prefer. And then solve the problem and make sure to be careful to use the correct units. And then check the result and say, is this reasonable? For example, if you get a speed that's faster than the speed of light, well, you made an error somewhere in the process. So whenever you get to the end of a problem, it's always good to ask, does this make sense? Because if it doesn't, then you might have a problem somewhere. So I believe that is the end of the chapter. Yes. So let's see. Okay. So I hope that that was informative. If you have any questions, let me know. If you want access to the PowerPoint, I might be able to link that somewhere, or you can just send me an email or talk to your teacher and you'll send me an email. So have a good day. And if you have any questions, let me know.